All right, AP Calculus, here we go into section 5.4, the Fundamental Theorem of Calculus, Part 1. As the savvy among you will have deduced already, the next section, 5.5, is going to be called Fundamental Theorem of Calc, Part 2. But hey, one thing at a time here. They decided to break this up. And let me preface all this by saying this is going to be one of those sections that I really bemoan the fact that we're doing this on video and not live in class, just because I like seeing the look on people's faces when they kind of put a few things together here mentally and realize this is some of the really cool material that we do here in AP Calc. Now, I have to preface again all this by saying that this is a section here where some of you already know what's coming. For those of you who've been waiting and waiting so far in Chapter 5 for when are we going to start doing integrals the right way, which they taught us at the end of pre-calc last year, and I think most of you saw that, this is where we're getting to it. But it's another one of those sections that from a practicality standpoint might not seem like much, and it might seem like more of a theoretically significant section, although I think it really has high marks in both of those categories here. So what we're going to start doing in 5.4 is starting to tie together two ideas that unfortunately were already introduced to you guys last year as being related. But I've got to tell you that in Europe in the 15 and 16 and 1700s, when mathematicians were developing this, they were totally separate. And the idea that there's a connection was really, really groundbreaking at the time. So what we're going to start off by doing, guys, is recalling just a couple of integrals from section 5.2. So these are in your notes already, 2 sections back. You don't need to write them down if you don't want to, but here we go. An integral from 0 to b of just x dx was going to end up being a b squared over 2. The integral from 0 to b of x cubed dx was going to end up being a b cubed over 3, and then the same integral for x cubed was going to end up being a b to the 4th over 4. Now, I'm writing those all down in succession right here just to wonder if maybe we didn't notice something that's happening here. That each time we go to integrate this particular integrand right here, that was kind of redundant what I just said, take a look at what happens to the x. Its power increases by 1, so it became an x squared, and then we divided by that new power. Then we just replaced the x with this upper limit of integration, and we ended up right over here with the b squared over 2. And the same thing happened right here on the second line when we integrated x squared, and the same thing happened on the third line when we were integrating x cubed. Now, if you recall, and I didn't make you guys do a whole lot of the grunt work on this, coming up with, actually, you know what, it wasn't that one. This was the one right here that we spent a long time and a very big slide walking through step by step in section 5.2. And I said, look, you guys don't really need to have this memorized. I'd like you kind of to be able to understand it as we walk through it, but it's not really something that you're going to need to know. Well, mathematicians 300, 400, 500 years ago, they weren't able to just assume. They weren't able to just dump it into their calculator or a computer. They had to do that really long and difficult grunt work there to figure out that this expression, and let me remind you guys that that expression right there used this newfangled symbol basically to represent a limit as n approached infinity of a summation, starting at usually k equals 1, but going up until n of this product right over here. And when you looked at it that way, these problems were a ton of work to arrive at this conclusion. But what someone noticed, and again, this sounds so silly and so obvious now, but trust me, it wasn't. What someone noticed is when I do all of that work to go from here to that result, and to go from here to that result, and to go from here to that result, somebody noticed that every time we do this, the answer we end up with, the 3 expressions I have in circles right there, they seem to follow a pattern. What just so coincidentally seems to happen is that the answers that we end up with end up being an antiderivative of the original integrand, or the function that we were evaluating to come up with the heights of all of our rectangles. So what was going on in the world at the time is you had some mathematicians worried about this expression right over here. Some mathematicians were worried about, hey, how do we approximate or find the area underneath a curve? Other mathematicians thought they were working on something completely different, the concept of antiderivatives, once derivatives had been developed a little bit earlier than that. And then, I don't know exactly how it happened, they must have been in an online chat room or seen it on Twitter, somebody realized that all of my results here from my area problems seem to match up with somebody else's results from over here in these antiderivative problems. And somebody, or a lot of people, put 2 and 2 together right here and realized that we can now evaluate definite integrals by using antiderivatives. Let me say that again. The realization, and Isaac Newton is the one who's really credited with putting all this together, him and a German guy named Gottfried Leibniz. Those two were really credited with being the ones who realized that you can do all of this messy work right over here. You can write it more easily this way, but you can evaluate it more easily using antiderivatives. Now again, this was spoon-fed to you guys last year in pre-calc, especially those of you who took honors, that you can evaluate a definite integral by doing anti-differentiation. But those were not developed with the knowledge that they were inverse operations of one another. They were two totally separate things, and then by dumb luck, they happened to meet. It's kind of like the Transcontinental Railroad, except there was no plan. It was just like, hey, one guy's building a railroad from the East Coast moving west, and somebody's going from the West Coast moving east, and hey, what a lucky coincidence, we met up. That's kind of what happened here. So, putting all this together, this is what you guys really need to have in your notes, and we're going to put a nice big box around it. The fundamental theorem of calc, part uno, says the following, everybody. That is the prettiest integral sign I've drawn in a long time. That the definite integral from a to b of a function, your integrand, f of x, taken with respect to x, is equal to, now you'll notice I have two equal signs here. I'm going to do this in two parts. What we're going to do here, guys, like we just said, is we're going to evaluate this definite integral by anti-differentiating our integrand. And the antiderivative of little f of x we talked about in 5.3 as being capital F of x. And now what we're going to do is introduce a notation that I may have talked about once or twice in the year, but you certainly haven't seen very often. We're going to put a vertical line after that expression, which I just simply call an evaluation bar. There might be a better name for it than that, I don't know. And then those same limits of integration from the definite integral, back here in the beginning, a and b, go here and here. Now, what does that mean? That evaluation bar means that you are going to take the preceding expression, which is capital F of x, and evaluate it first at its upper limit of integration. Then you're going to evaluate it at its lower limit of integration and subtract the results. So this is going to be capital F of b minus capital F of A. Just barely fit that in there. All right. And this, everybody, may not look like much, but that is the fundamental theorem of calculus part 1. Now, I'll tell you right now, most of the time you see this written out, that middle step will be skipped, and people will go directly from the first step over here to the second step. And that is perfectly fine. I just kind of wanted to use this opportunity to show an evaluation bar and explain what it is, and this is how it works. So again, it is so easy for us to be, what are the words here, guys? Ethnocentric, to have recency bias, to stand on the shoulders of geniuses and say, oh yeah, I mean, obviously, duh. But I can't stress enough what a huge breakthrough this was in the mathematical sciences at the time, made primarily by Newton and Leibniz, to recognize that an infinite sum, that being a definite integral, could be evaluated by using antiderivatives. Okay? At that time, integrals and antiderivatives were not known to be the same thing, the way that some of you guys learned it last year and the way we kind of talked about in 5.3. This was a huge breakthrough that really made a lot of very cool and very difficult things in math not only possible, but pretty darn efficient, as we're going to see right here. All right, so guys, go ahead and put a big box around that. Let's make it festive. We're going to go with this nice fuchsia color, and we're going to make this big and bold, and there we go. All right, so here it is, guys. Boom, and boom, and boom, and boom. And there's Fundamental Theorem of Calc Part 1. Okay, so big things popping, everybody. Now, that's really the theoretical development right here of what's happening in 5.4. Let's start to look at this practically. Okay, and we're supposed to evaluate each definite integral using FTC Part 1. Poor spacing on my part. All right, so if we think about what's going on in this problem, you guys know me. I love to start you, when we learn something new, I love to start you with an example that we're going to do two different ways. And hopefully, we're going to get the same answer, because this is math and not English, everybody. It's not a question of your opinion. So let's take a look at what's going on here. We are trying to integrate a linear function, negative 2x plus 3, on the interval from 0 to 5. And because this is a linear function, geometry will work for us, everybody. Let's see what we know. This function has a y-intercept of 3. So I'm going to go up here, and I'm going to make a y-intercept right there at 3, and a slope of negative 2. So down 2, right 1, down 2, right 1. Okay, I think I get it because I'm pretty good with linear functions. Go me. All right, so there's our function. And we want to know the net or signed area starting at x equals 0 and ending, I don't think I drew this real well, but that's okay, over here at x equals 5. So that gives us one triangular region above the x-axis and one triangular region below. And I probably should have labeled things a little bit better. So this over here was going to be at 5. Let's think about this real quick, although I don't want to dwell. Our x-intercept right there, the value of x that would make y equal 0, I do believe is going to be 1.5 or 3 over 2. Gotcha. And this ending y value right down here, I would just evaluate the original function at x equals 5. Negative 2 times 5 is negative 10, plus 3 is a negative 7. So what do I know using geometry, everybody? The integral from 0 to 5, and I'll just call this f of x now to save some space, is equal to, okay, the area of the triangle on the top is 1/2 times a base of 3/2 times a height of 3. And then we're going to subtract the area of the triangle on the bottom because it's entirely below the x-axis. So its area is going to be 1/2 from 1.5 to 5. Means we have a base of 3.5, which is 7 over 2, and a height then of 7. I didn't put negative 7 because I already used a negative right here. All right, I didn't leave myself a ton of room, but what happens here? Looks like that first one, I guess I'm working up here, guys. That first one is going to be 9 over 4 for the area of the triangle on the top, and then minus down on the bottom of 49 over 4 for the area of the triangle underneath. So, mathematically, that gets us a negative 40 over 4, which looks like negative 10 is going to be the answer that we would have come up with back in section 5.2. And it wasn't really all that bad. But welcome to section 5.4, everybody, where now we are armed with what we think is fancy new information. Fundamental Theorem of Calc Part 1 tells us that we can evaluate a definite integral using antiderivatives. So let's try this, everybody. We are going to anti-differentiate the expression negative 2x plus 3, and with its a polynomial, we're simply going to reverse the power rule. So the x stays put. We raise the exponent by 1. It was x to the first power. It now becomes x to the second power. And then we divide the old coefficient, negative 2, by the new exponent of 2. And negative 2 divided by 2 is just a negative 1. Check that real quick. The derivative of negative x squared, is negative 2x. So we're in good shape. Then we're going to add to that the antiderivative of 3. 3 being a constant, all we have to do is stick an x at the end of that. Now, normally, with an antiderivative, we would put a plus c right here. And I'm going to do it just this once to prove a point to you guys. You will never see me do it again, and I'll show you why in a moment. So what we have here, negative x squared plus 3x plus c, that is our antiderivative here. all right, of negative 2x plus 3, and we now put an evaluation bar, and we evaluate this expression, really, I should say it this way, from 5 to 0. You can say from 0 to 5, but my point here is that if, according to the formula, we begin now by evaluating capital F of b. Okay, so we're putting a 5 into this expression right here. So I'm going to go slow with this one, guys, and it's a really good idea to keep your thinking segmented, okay, to use brackets or parentheses. So I have got the opposite of 5 squared, which is not the same thing as negative 5 squared, everybody, plus 3 times 5. And remember, guys, that 5 is a value of x. We don't know the value of c, so I just leave it as plus c. Then we subtract from that the expression capital F of a, and we put a 0 in there. So that is going to be the opposite of 0 squared plus 3 times 0, and then again a plus c right there. And let's see where we're at now, guys. The opposite of 5 squared is a negative 25, plus 3 times 5, that's a plus 15, and then a plus c. Now, lucky for us, that's a 0, and that's a 0, and all I'm doing now is distributing this negative all the way over there to get a minus c. And where are we now, everybody? Well, the reason I told you guys it wasn't necessary to put this plus c right here is because of what happens right here, and I promise you it will happen every time we do this. Whatever c value it ends up being, and we have no way of knowing, you're going to be subtracting the exact same c value right here, so those just cancel each other out. And we end up with a negative 25 plus 15, which sure enough is a negative 10. Exactly the same answer that we got here doing the problem geometrically. And for some reason, and I can't remember why, that little red thingy right there is the answer to this that I had written down and shrunk down at some point. Let's see if I can get that to open back up. Nope. I think, oh, for crying out loud wise. There we go. The answer I was looking for was negative 10. I'm not sure why I had that there, but hooray, everything matches up. Okay. So, what is the point we are trying to prove here, everybody? You can do this problem either way. You can do it geometrically, which we did down here on the bottom, or you can do it calculitically. I'm not sure that's a word. But anyway, we can do it using the fundamental theorem of Calc Part 1, and we get the same answer either way. I would pose the rhetorical question right now to you guys, which way seemed easier to you? I wouldn't be surprised if you guys told me that here, the geometric method seemed easier. I wouldn't even argue with you about that. But I think you know what's coming, everybody. In just a moment, like, oh, I don't know, maybe right now, we're going to start to do this with a function that's more complicated, with a quadratic function. And a quadratic function, everybody, is much more difficult to find the area underneath geometrically than this linear function was. But what you'll find is with the calculus method, it's really not a whole lot more work. All right, so the point I wanted to make here is there's more than one way to skin a cat, and you can do this particular problem either method, geometrically or with FTC Part 1. So I wanted you to see that. I also wanted you to get a decent level of confidence right now saying, maybe this FTC Part 1 thing actually works because we're 1 for 1 right now. I got the right answer. All right, so good. Let's take a look at this problem now, guys. And the more practice we get with the fundamental theorem of Calc Part 1, the faster we're going to become at it. All right, guys, we're doing a definite integral of a quadratic function taken from 2 to 5. So here we go. Let's anti-differentiate. The first term's antiderivative, everybody. We start with an x, raise the power by 1 to get an x cubed, and then divide the old coefficient, 6, by the new exponent, 3. And 6 divided by 3 is going to be a 2. All right, that's our first antiderivative. Then the next one, guys, we've got x, and we're squaring that. We're raising it by a power of 1, and we divide the old coefficient 2 by the new exponent 2, and that's just going to be a minus 1 for our coefficient. The 3, again, is a constant, so that becomes a plus 3x, and that's it for the antiderivative. I'm not going to bother writing a plus c, but I put my bar there, 2 on the bottom, 5 up on the top. Check yourself real quick. does our derivative now match the original integrand? The derivative of 2x cubed is 6x squared. The derivative of minus x squared is minus 2x. The derivative of plus 3x is plus 3. So yeah, we're in good shape. And now let's start putting in the 5. And again, I like to do brackets to keep everything separate. And I'm going to start going a little faster here, guys. I can do some of this stuff in my head. I think you can too. 5 cubed is 125 times 2 is 250. Minus 5 squared is 25. Plus 3 times 5, that's a plus 15. Close it off. That's the end of f of b. Minus, and now we'll do f of a, plugging a 2 in there. 2 cubed is 8 times 2 is 16. Minus 2 squared is 4. Plus 3 times 2, which is 6. All right, where does this get us? 250 minus 25 plus 15 is going to be a 240, I'm pretty sure. And then minus 16 minus 4 plus 6 is going to get us 18. So I've got 222 for my answer here to that definite integral problem. Okay. Not too bad, guys. Not too shabby. 2 more I want to do with you. Ooh, how about trig integration? This is yet another one, everybody, where trying to do this geometrically would be very, very difficult to do for the simple reason that we don't have a formula, at least not the formula that I think you guys know, for how to find the area underneath a sine or cosine wave. But let's see what's going on here, guys. We know that our cosine wave, I hope we know that our cosine wave starts up here at the point 0, 1. And we know that cosine comes down and then goes back up and does kind of the same thing over here on the side. And I maybe didn't label that really well, but okay. We're evaluating this thing from negative pi over 2 to positive pi over 2. And the significance of that, negative pi over 2 is your first x-intercept on the left. Positive pi over 2 is your first x-intercept on the right. So we are interested, everybody, in the area of that one hump of a cosine wave. And again, to my knowledge, I don't think you guys know a formula for that. So this is going to be new for all of us. How do we do it? We integrate by anti-differentiating our integrand. What function has a derivative of cosine of x? That is just going to be sine of x. Pretty as you please. Evaluate it here from negative pi over 2 on the left to positive pi over 2 on the right. So where are we going here, guys? Let me write this out here, although some of you will be able to skip this step. This is going to become the sine of the upper limit, pi over 2, minus the sine of the lower limit, which is negative pi over 2. What does that do for us, guys? Sine at pi over 2, again, back to my unit circle right here. Pi over 2 is right up here. Sine is my y-coordinate. That's 1. Minus the sine of negative pi over 2. Right here, my y-coordinate there is negative 1. And 1 minus negative 1 is 2. Now, the reason I'm being funny about this, that is certainly not an interesting answer. 2's about as boring as it comes. But I want you guys to realize what we've just said. This area of that one region right there that I shaded in red, let me do it the other way too for emphasis right here, that region underneath one hump of a cosine wave with an irrational base right here of pi units, with a height of 1, but with all of these irrational y values going on right there, the answer to that ends up completely rational, and it's just 2. That's one of those things, you guys, that kind of makes me go, whoa, something spooky's going on right here. Not spooky, that's not the right word. But to me, this kind of fills my soul with this wonderful, benevolent, benign, just thing like, wow, math works, man. And even some of the weird, ugly stuff that we have out there, like a cosine wave with all of these crazy values all over the place, things work out nicely within there. And the area of that one hump of a cosine wave is equal to a nice clean number like 2. And then I sleep very well at night because I know that the universe works and makes sense. And I'll die someday, but my body and my kinetic energy and whatever will go back to the earth, and conservation and math and numbers will continue to go on. And if that doesn't make you feel good, everybody, I don't know what to tell you. Anyway. Last one right here. Let's knock this one out. Let's do an integral of an exponential function, e to the 2x. All right, and we're integrating this thing from 0 to a very ugly irrational number of the natural log of 3. So let's get to it, guys. We can do this by anti-differentiating e to the 2x. Okay, how do we take an antiderivative of an exponential function? Same base, e, to the same power, 2x. Now, when we differentiate, we multiply by the derivative of the exponent. Now that we're anti-differentiating, we are going to divide by the derivative of the exponent. The derivative of that exponent is 2, and so dividing by 2 or multiplying by 1/2, same thing. An evaluation bar here goes from 0 to the natural log of 3. Now when it's time to evaluate that, I'm going to go ahead and do one thing that you guys probably don't often do, and that's fine, but I'm going to go ahead and put a bracket. I thought I was going to put a bracket right there. And you'll notice I left the 1/2 out. That 1/2 is a constant that is unaffected by these two values that we're about to put in here for x. So what I'm going to do on the next line is just keep the 1/2 here and then in brackets start what's happening next. And while I'm at it, let me go ahead and tell you guys a little historical thing. The evaluation bar is actually the evolutionary remnants of a right bracket. This is actually the way it was originally written, and I don't know what mathematician or plural mathematicians coined this phrase or started this convention. This is the way it used to be written, and then eventually they just left off those little horizontal pieces, and there you go. Anywho, okay, where are we now? We're going to leave the 1/2 out, and we are going to evaluate e to the, and the 2x now is going to become a 2 natural log of 3. Minus an e, and the 2 times 0 is just going to get us a 0 for that power. Now, where are we here? That expression right there is one that I'm hoping you guys know how to evaluate. E and natural log cancel each other out. The problem is the 2 in front of the natural log. So I'm going to use that property, guys, that says you can get rid of a coefficient of a log and make it an exponent on that product right there. So this first term now becomes e to the natural log of 9, and in this case, the e and the natural log are right next to each other. They will cancel each other out, and we're just going to end up with a 9 right there. Minus e to the 0 power is going to be 1, and we're going to end up now with an 8, and half of that 8 is going to get us 4. Okay, and last thing I'm going to say, I promise I won't dwell on this. Think about what's happening here. We have yet again a goofy, irrational function, everybody, e to the 2x, which really doesn't look a whole lot different than e to the x. It just increases a little bit faster. Whole bunch of irrational values. But if we start this thing at 0 and end it at the natural log of 3, e to what power is 3? It would be just a little bit more than 1, everybody. But that value right there is the natural log of 3. This region here has a nice, clean, rational area of 4. This is an example of how sometimes I choose to make a problem ugly at the beginning, but the reason I do it is because I want the answer to work out nicely at the end. All right, ladies and gentlemen, that's as much as I wanted to subject you to in terms of torture here from section 5.4. Hopefully you think that one's not too bad. This, again, was a big theoretical jump. I think practically you guys are going to do just fine with how to utilize this newfound knowledge. So good luck, and let me know when you guys have questions on 5.4.